and welcome to NASA headquarters. Today's briefing will discuss the upcoming March 12th launch of NASA's Magnetospheric Multiscale, or MMS, mission that will study magnetic reconnection around the Earth. Now that's a lot to swallow, but remember these two words, magnetic reconnection. What is it? Why is it important to study? Today, you will get those answers. All of the information you will hear today and any updates will be on the website at www.nasa.gov/MMS. And also, for the social media folks out there, there's a lot of excitement building for this launch. Send your questions in at #AskNASA and follow the conversation. It is growing and growing about this upcoming launch and the unprecedented science coming from this mission. Twitter, Facebook, and other social media platforms. We'll have brief presentations from our participants, and then we'll open it up for questions starting here in the NASA TV studio, our phone lines, and the questions from the public viewing this program on social media. First, let me introduce you to today's participants. First, you'll hear from Jeff Newmark, Interim Director, Heliophysics Division, NASA headquarters in Washington. Jim Birch, Principal Investigator, MMS Instrument Suite Science Team, Southwest Research Institute, San Antonio, Texas. Greg Dulli, MMS Project Manager at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And Paul Kasich, Associate Professor, West Virginia University in Morgantown. And with that, we'll start with Jeff.
Thank you, Dwayne, and good afternoon, everyone. I'm really thrilled to be here today to introduce MMS to you all. Before we talk about MMS in detail, I want to step back a little bit and talk about how it fits in with the important work that NASA is doing on heliophysics. Heliophysics is kind of a strange word to many of you, but it deals with some of the most fundamental parts that we know, starting with the sun. We all recognize the sun. And what we're doing is looking at the sun and its extended atmosphere that we call the heliosphere, and how it interacts with the planets, the space environment around the Earth, the space environment around other planets, out to the edges of our interstellar space. The sun is actually variable. Many of you think of the sun as a constant, but if you look at this first movie I have here, you'll see what we actually, when we look at NASA, look at the sun at, you see these activity zones. You see large eruptions of the sun we call solar storms. These storms travel throughout interplanetary space, and at times these storms interact with the Earth. And that interaction can cause what we call space weather. What starts these storms? What causes the space weather around the Earth? This is a phenomenon that Dwayne already mentioned, magnetic reconnection. Magnetic reconnection actually occurs throughout the universe, not just on the sun, not just around the Earth, but around other planets, at the edges of our solar system, and in fact around black holes, large other galaxies. This is a fundamental process that occurs, and MMS is going to revolutionize our understanding of it. In that movie, we saw it as a very large-scale system, looking from the sun all the way through space to the Earth. How do we study that system? The next graphic you see here shows you our heliophysics system observatory, the fleet of spacecraft that NASA uses to look at this connected system. We're studying the sun, how the solar storms erupt from the sun, how they travel through space, how they interact with the Earth's magnetic environment. And so we need this whole system together. MMS is going to fill a key part of this new system. If you look at my next view, you'll start to introduce you to MMS. What is MMS doing? It's going to actually fly in the Earth's magnetosphere, this protective magnetic environment around the Earth. And you can see here the observatories. We're using this environment around the Earth as a natural laboratory. We've actually, rather than building one on Earth, we're going to where these magnetic reconnection actually occurs in space, so we can understand it. You'll see here, as you see, we have 4 spacecraft. which gives us a three-dimensional understanding, and in fact, a four-dimensional understanding. You'll hear about the instruments that revolutionize our ability to make measurements in time as well as in space. To tell you some of the details about it, I want to introduce Dr. Jim Birch.
Thank you, Jeff. Sunlight and starlight ionize the thin gases that fill the solar system and galaxies. In this so-called plasma state, electric and magnetic forces are stronger than gravity, and many dynamic phenomena occur. The most energetic of these is magnetic reconnection. It occurs when magnetic fields and adjacent regions of space interconnect. In the process, magnetic energy is destroyed, and heat and kinetic energy are released. Because of its explosive nature, magnetic reconnection is often described as a magnetic explosion in space. Reconnection is important to us as the engine that drives space weather and a main disruptor that is frustrating our attempts to harness nuclear fusion with magnetic containment devices. The MMS mission will conduct a definitive experiment in space that will finally allow us to understand how magnetic reconnection works. Let's look at a video. Magnetic fields exist throughout the universe, and energy is often released by magnetic reconnection. In the outer parts of our galaxy, or at the center of our galaxy, there's a black hole, and these are X-ray flares that have been observed recently, caused by reconnection. In the sun's superheated corona, magnetic fields create spectacular loops and arcades. The energy stored in these structures can release, creating explosive solar flares and coronal mass ejections. Intense fluxes of energetic particles and giant clouds of ionized gas and magnetic fields are ejected from the sun and travel throughout the solar system. When these clouds impact other magnetic fields, such as the Earth's, similar reconnection events occur, and these cause intense magnetic activity and the auroral lights. At the same time, they accelerate charged particles to high energies, creating a hazard to space travelers and spacecraft, and even disrupting ground-based power grids. Magnetic reconnection also occurs in laboratory devices, and this is a major magnetic storm at the Earth producing the aurora. In the laboratory devices that are designed to harness nuclear fusion by heating up the plasma confined by magnetic fields, events called sawtooth crashes have thwarted efforts to permanently solve the energy crisis. Now, next slide shows a simplified picture of reconnection. A fundamental question is why and how does magnetic reconnection take place? The answer is in one sense simple, but in another sense complex and mysterious. The simple part is that adjacent magnetic fields pointing in opposite directions tend to annihilate each other, releasing their magnetic energy and heating the charged particles in the surrounding environment. In this process, magnetic reconnection, the magnetic fields are torn apart and reattached to their neighbors. The mysterious part is what goes on inside the box labeled diffusion region. With MMS, we will be able to probe the diffusion region for the first time with measurements down to the smallest scale of the plasma, the electron scale, to solve this mystery. Now, the next animation is going to show reconnection simulations. This is the magnetosphere, solar wind coming in from the left. There are two boxes. These are our targets on the day side and one in the tail on the right. Inside these boxes, reconnection is going on, and this video shows, or this animation shows, one of the latest and most sophisticated computer simulations of the diffusion region. We know what goes on outside of this box from some previous missions, but what goes on inside the box is a mystery, even with the simulations, because they cannot simulate everything. Computers are not big enough. And so we have to fly spacecraft in that box, and we have to put 4 spacecraft in there and make particle measurements 100 times faster than have been attempted in previous missions. Now, this is our orbital strategy. The video showing the launch of the satellite, the 4 spacecraft in a pyramid configuration. Launched on the night side, we spend 6 months getting the instruments ready, and then we scan through the day side along the magnetopause where reconnection is occurring, adjusting the spacing between the spacecraft down to a minimum of 10 kilometers, and we make 2 scans through the day side. At this point, we raise the apogee to 25 Earth radii and make 1 scan through the magnetotail, also adjusting the spacing between the spacecraft. Now, to tell us how we accomplish this with the spacecraft is Craig Dulli, project manager.
Good afternoon. I'm going to talk just a little bit about these incredible machines that we've built and how we're going to fly them to create this in situ flying laboratory that the gentlemen have just described. In my first photograph, which you can see, you'll see the 4 MMS observatories in the clean room at Goddard Space Flight Center. Indeed, at Goddard Space Flight Center, where we designed and built and tested these observatories. The instruments, and there are 100 of them, were led and brought to Goddard by the Southwest Research Institute, where we then integrated them with these 4 observatories. And you can see in the picture, the red covers show you some examples of the instruments and such, and there are covers on the solar arrays. Now, in the next photograph, if we could bring the next one up. You see the stack where you can actually see the solar arrays and the instruments on the top edge of that octagonal perimeter. And we're flanked there by the 2 halves of the Atlas fairing, the 4-meter fairing. Each of those MMS spacecraft weighs just shy of 3,000 pounds. About 900 pounds of that is fuel we carry. And they measure each about 4 feet tall by about 12 feet across that octagonal cross section. A couple things that are very special about MMS, and indeed some of the challenges we faced in building them, and some of the reason that we built them ourselves at NASA, is in order to make the measurements that were described, these very precise magnetic field, electric field, and particle measurements, our own spacecraft have to be very, very clean, meaning they can't have very much a significant electric field or magnetic moment of their own. We don't want to see our own noise. So we've built spacecraft in this case that are have about more than 100 times lower residual magnetism and more than 1,000 times lower than what is typical for spacecraft to have in terms of electric charge. So every aspect of these spacecraft was designed to be very clean so we can make these precision measurements. The other aspect of these is these are spinning spacecraft, as was mentioned, so they have to be precisely balanced. Even as we deplete the fuel, they have to be balanced because we need to keep, and in this little model of MMS, we have to keep these very precisely oriented with respect to the ecliptic north of our solar system, all the while spinning. Now lastly, this is a fairly large stack, and when we stack it up, when you saw it, it's about 16 feet tall. But in this picture, what you can't see is when we deploy these, we then extend sensor booms from each one of these. We deploy 16 feet of magnetometer booms. You'll see those unfold in a video in a moment. We then also extend 50 feet of booms out along the spin axis this way. And then we finally, on 4 sides, put out almost 200 feet of wire booms with sensors on the end. All of these booms then enable us to measure in 3 dimensions the electric fields and the magnetic fields. We do all this with spinning spacecraft that we're flying in a formation as close as 10 kilometers. To give you some sense of scale, once we've deployed these booms, an MMS footprint is about the size of a full baseball field. So we end up flying 4 baseball fields, kind of in a distance that ends up being about the size of Washington, D.C. separation when we're 10 kilometers apart. In the video we'll show next, and we can bring it up and I'll narrate it. I'll describe a little bit about what our only a few weeks from now is going to look like. That's the Atlas rocket on the pad. Of course, that's our launch vehicle. In some aspects of this video are sped up, otherwise this press conference will be very long, and I'll comment on that when you see them. But there's our launch on the Atlas V. Here you'll see the booster separate. In the Centaur upper stage will carry us on our initial orbit that Jim showed you. The fairing separates, which we detect, and there's our stack of 4 MMS spacecrafts already spun up by the Atlas Centaur. Now you'll see them start to separate from the top down. In actuality, it's about 5 minutes between the separation events as we get the separation distance we want initially. We sped it up here to show you. And here you'll see that first 16-foot magnetometer pair of booms deploy outward on the bottom side of the spacecraft. And then shortly we will see the example where we start releasing those 200-foot wire booms out the side, all the while spinning, all the while keeping this thing very, very stable. And then finally in this video you'll see those spin axis or axial booms deployed upward. They uncoil their folded coil booms, leaving us with these very large spinning spacecraft in a formation that forms this laboratory. And as this video rolls on, another liberty with the video is you can begin to see other MMS in the picture. I don't think you'd see them quite this well at 10 kilometers, but you get the idea. We are flying these 4 spinning, very large, once deployed spacecraft in formation. We maintain that formation to an accuracy of 100 meters. So we're flying 10 kilometers apart using the GPS on the that is actually below us, a GPS system we built. We keep track and maneuver this formation to within 100 meters. Now, to talk a little bit more about the bigger picture of what we're doing with MMS and how it fits in the bigger picture of heliophysics, I'll turn it over to Paul.
Thank you, Craig. So I'm really excited to talk to you today about why scientists are waiting with bated breath for MMS to be launched, and why everyone should also be excited about what we're going to be able to learn. So the first M in MMS stands for magnetospheric. The Earth has a magnetic field that sticks out into space, and the part of space where the magnetic field is dominant is called the magnetosphere. Outside the magnetosphere, you have particles from the sun being spewed out. That's called the solar wind. And those particles that would normally run into Earth, instead they run into the Earth's magnetic field. So the Earth's magnetic field is very important in protecting us from the particles from the sun. So shown here in my first graphic is a sketch of the Earth's magnetosphere, which comes from a computer simulation. The Earth is the ball in the middle, and the strange-looking yellow lines represent the magnetic field. The lines connecting to the Earth in the center are the magnetosphere. And on the left you see a magnetic field line, and that one is being pushed in away from the sun by the solar wind towards the Earth. So as we've heard from the other panelists, the MMS mission is designed to study magnetic reconnection using the magnetosphere as a laboratory. It occurs when oppositely directed magnetic fields point in opposite directions and they come together and effectively break. So we will see this in motion in a moment. Magnetic fields from the solar wind in this animation will come in from the left side, and when they reach the magnetosphere, they'll break, and that's what magnetic reconnection is. So let's go ahead and roll the animation. So you can see the field lines coming in from the left and breaking when they reach the magnetosphere, and that's magnetic reconnection. But the process doesn't end there. You see these magnetic fields being dragged away from the sun, and when they get to the far side of the Earth, the field lines are oppositely directed again, and they break again. That's, again, the process of magnetic reconnection. And you can see what happens is the magnetic field lines shoot back towards Earth, and that's where it gets interesting for us. So the magnetic fields snap back like rubber bands and blast these hot particles back towards the Earth. So as we saw in Jim's animation, some of these particles harmlessly run into the atmosphere at Earth. And when they do, they excite the gas up there, and the gas ends up giving off light, and that's what we on Earth see as the northern and southern lights, also known as aurora, as pictured here. However, as we've also heard from the other panelists, the particles can cause problems too. So there's a number of satellites in space that we use for very important things like cell phone communication and GPS. So if these particles run into the satellites, they can short out the circuits and can knock out the satellites, and that would cause problems for cell phone reception. The moving magnetic fields can also drive electric currents on the Earth, and that can overload transformers and lead to power outages, which has happened in Canada and the United States and parts of Europe. So all of these are aspects of what are known as what's known as space weather, and so you can see that magnetic reconnection plays a very important part in space weather, and that's why it's important for us to study the fundamental science of magnetic reconnection in order to understand it. So that's just one reason that MMS is important to all of us. So why is MMS so important to scientists? So going back to the name MMS, the second M and the S stand for multiscale. This signifies that reconnection happens at a very small region in space, as we saw in the animation, but it impacts a huge region of space of the whole magnetosphere, which is 1 million miles long. This makes it extremely difficult to study, so like a cosmic version of finding a needle in a haystack. The best we've been able to measure magnetic reconnection in the magnetosphere has been with a mission with 4 satellites in a pyramid and they were separated by 600 kilometers or more. So 600 kilometers is the distance from Washington, D.C. to Boston. But as we've heard from Craig, the 4 spacecraft for MMS will be separated by only 10 kilometers, which is about the size of Washington, D.C., so much closer than we've ever been able to see before. In addition, as we've heard, we'll get the data much faster than we have in the past, 100 times faster than previous missions. So to get a feel for what this is like, picture watching a football game, and you can watch for a minute at a time, but you have to wait an hour in between times that you can watch. It would be really hard to figure out what's going on in the football game. So these are the problems that have been plaguing researchers studying magnetic reconnection, is that we can't see the smaller scales, and we can't process the data fast enough to really understand what happens right at the place where magnetic reconnection happens. So this makes it difficult to see, for example, how particles get accelerated and heated during magnetic reconnection events. So you can see NASA's MMS mission is really going to give scientists an unprecedented opportunity to study reconnection. Go back to Dwayne.
Thank you, Paul, and folks. Okay, so let's see if we can go ahead and go take questions. We'll start with, we're here in the NASA TV studio with the question here, and then we'll go to the phone lines, and then we'll go to social media. If you can wait for the microphone, say your name and your affiliation, please.
Adam Minster, Medill News Service, and actually a question for Greg. You mentioned the 4 different shuttles that are being used. Can you explain why specifically there needed to be 4, and whether kind of these 4 shuttles flying so close together is a norm and something that typically is done?
Oh, okay, so but they're spacecraft or observatories, but I wouldn't call them shuttles. All right, I mean, we have 4 MMS spacecraft. There's a model of them there, but the reason we have 4 is as we've talked about, we want to measure this phenomenon. We want to capture it in 3 dimensions. And so if you just kind of imagine, if I've got 3 things, no matter how I put them down, they'll define a plane. I can only get 2 dimensions with 3 objects. So in order to have 4 measurements simultaneously of whatever's going on, I really need to have at least 4 points in space. And that's what we talk about in making a pyramid. There's 3 of them and another one here. So now we have a 3-dimensional, shall we say, sensor made up of 4 satellites, so we can know what's going on in 3D, and we also know what's going on very fast in time.
These be used for anything else other than magnetic studies in the future?
No, this mission is dedicated, and indeed we anticipate it will largely solve the mystery of magnetic reconnection, but it's a mission dedicated to that. They'll fly for 2 years, possibly more if we decide to extend the mission, but their sole purpose is to probe and really understand and solve the mysteries of magnetic reconnection.
Okay, we're going to kind of switch gears here. We're going to go to social media, and Karen Fox, who's on the board there, what's going on in the community? What questions are coming in?
We do have some questions for you. At Bone Drake has asked us, she's been studying SMAP, a recent NASA mission, in her high school global studies class. She's wondering whether MMS will be related to that. And then the question is, how will MMS data be connected to some of the other missions that we have?
So this is Jeff Newmark. I'll take that. SMAP is an Earth science mission looking at soil moisture, and this mission is not really related to that. It really is looking at a very different phenomena. It's really looking at the environment, our near space environment, where SMAP is looking down at the moisture in the soil throughout over the Earth. In terms of how the data works together, again, what I showed you earlier in the video, we have today spacecraft that look at the sun, look at the initiation of those solar storms. We watch those storms travel through interplanetary space, going towards the Earth, and then we don't really know what happens as they interact with the Earth's magnetic field. So we use the other spacecraft to set up the context, and that allows MMS to then study the details of what's going on in that magnetic reconnection zone that you heard so much about.
We have any other questions? We'll take 2 more from social media, and then we'll go to the phone line, and we'll come back.
Another question from @BeastMode. Wanted to follow up on the GPS that Craig Tooley mentioned. Can you describe how MMS uses GPS and relies on it, please?
Sure. Our GPS system, and it's actually got a name. It's called Navigator, which is quite fitting. The way it works is, much as we use GPS on the ground, as you would use in your handheld or in your car or on your phone, we use it to determine our location of each observatory, which is very important because that's how we begin to understand where we are in these orbits. Because essentially MMS flies 4 very similar but not identical orbits all the time in order to maintain that formation. You can imagine 4 orbit lines that are very close. So we need to know precisely where each one is in relation to the Earth. Now the thing that is very, very novel and actually interesting about MMS's GPS system is the GPS constellation is far below us. We are much higher than that constellation of GPS satellites, and so our system is able to actually pick up very, very weak signals from the side lobes, of those GPS satellites, and from that it can triangulate and determine where each of our MMS satellites is. It also gets very precise timing of when we're there, and then that is continually, we send that to the ground. We use that then to design and plan the maneuvers that actually adjust the formation to maintain not too far apart, not too close together, and the right shape. And incidentally, as we do that, we get feedback from the science team. It's not something we've known in advance. One of the interesting things about the mission is we'll be fine-tuning that separation in order to optimize as we see the data. They'll be looking at this data real time throughout the mission, and we'll be tuning that laboratories to collect the data.
One more, Karen, and then we'll go to the phone lines.
All right, another question from @GalaxyGallius. The question is, what do we expect to be the lifespan of MMS, and do we think that the sun's radiation could have an effect either on the mission or on the data?
The MMS mission is actually nominally planned for 2 years of science gathering. It's preceded by 6 months, as Dr. Birch described, as we wait for our orbit actually to get around into that region of interest in the magnetoplasm front. We'll swing through that magnetopause twice, and then we will double our orbit size, our apogee, our farthest point, and we'll swing through the tail. And that's the 2nd year. So this is essentially a 2-year science campaign. We carry fuel, so if it makes sense, and there's and still something to be done, we could potentially do some more work afterwards if NASA decides that's warranted. So we won't run out of fuel quite that soon. In terms of the radiation, although magnetic reconnection sounds very explosive, and it is, from the standpoint of the electronics and such we have built on the spacecraft, these orbits, this region in space, is fairly typical of what we see for satellites. In fact, some of the time it's less severe than what geostationary satellites see as we pass in and out of the radiation belt. So in terms of radiation, this is a typical kind of environment for us to build science satellites in.
Okay, if you just joined us again, we're here at NASA headquarters learning about the upcoming NASA mission to study magnetic reconnection around Earth, and it is the first, I believe, dedicated project to do this. Very extraordinary science. So we're going to go to the phone lines to our media, and I believe we have Ken Kramer from Universe Today. Ken?
Hi, thanks for taking my question. Wonder if you could talk a little bit about studying, would it be worth studying the magnetosphere anywhere else in the solar system, at any other planets? And how do the other planets compare to the Earth? Thanks.
I can take that question. In fact, we are studying reconnection at other planets. Cassini at Saturn, for example, and then Jupiter, also reconnection is going on. But the mode is different because these planets are dominated more by rotation of the planet. And so the solar wind has an influence, and reconnection has an influence, but it's not as strong as it is at the Earth. And so it's a different type of circulation that is set up in these planets. But people like myself who work on reconnection, we do that at Saturn as well.
And I might also add that there are other missions have observed, and we've learned about magnetic reconnection in other regions of our magnetosphere, although we haven't flown into it. They asked about other regions on the Earth.
Oh, you did? Well, here we have 2 missions that have been up a while, 7 to 10 years. It's the European Cluster mission and the NASA Themis mission. And those are still operating. And they'll be operating in different parts of the magnetosphere, and this is where we'd be able to do a global study of what reconnection causes. As Paul mentioned, reconnection happens in this small region, but it affects the entire magnetosphere. And by comparing our data to the Themis and cluster data, we'll have a very powerful thing that we call the heliospheric observatory, or this will be a major part of the heliospheric observatory.
This is Paul Kasich. Just to add, also, the Messenger satellite mission is measuring reconnection at Mercury, and Mercury is a lot like Earth, except it's smaller, and so everything that we just described happens about 10 times faster.
Okay, there's a lot of buzz in the social media atmosphere. We're going to go back to Karen Fox again. If you have any questions, send in to #AskNASA. And Karen Fox, what have we got going on, coming in now?
We have a question from @MMontard, who wants to know, how does the spinning of the spacecraft interact with the sensors? How do you control the data given that everything is spinning?
You want to start with that one?
Yes, thank you for that question. Most of our measurements are independent of the spin, and this is how we make these very fast particle measurements, because we're not tied to the spin of the spacecraft like just about all previous magnetospheric missions have been. So we have a lot of instruments, and we don't care what the spin rate is for our particles, or low energy particles. So some of our measurements do rely on the spin. These long wire booms that Craig talked about need to spin for centrifugal force, because otherwise these wires wouldn't be stretched out like that. So we need the booms to deploy our antennas. The spin of the spacecraft is a pretty slow spin rate compared to most magnetospheric missions. I don't know if that answered the question completely.
I think we're back to me. We have some fun questions that are going a couple other directions, but I'm going to throw them out to you all. One of the questions from the Raisin 22 is there a chance that the magnetosphere around Earth is connected to a magnetosphere around a black hole at the center of our galaxy?
Paul.
I can try to answer that. So, Paul Kasich. I would say that they're not connected in terms of touching each other. I think where we hope the connection is that if we understand the physics of reconnection here near Earth in the magnetosphere, then we can apply what we've learned here in the magnetosphere to other places that reconnection happens, such as in solar flares, like we saw the movies of, other planets, and even in black holes and neutron stars.
We'll take one more from social media. Go ahead, Karen.
Great. @BillWaldman808 asks whether this mission is going to provide a model that can be used to predict space weather events in the future.
Well, this is a research mission, and what we learn from it will be an important part of models that will eventually be able to predict space weather. We won't be predicting it from this mission, but we will be coming up with theories, and we'll be proving theories that then can be used in models to make them better. In fact, I think it's crucial that we understand magnetic reconnection, because, as I said earlier, reconnection is the engine that drives space weather. So if you're going to predict what's happening, you got to understand the engine.
Right now, and I got a comment to follow that up, just more generally, as people think about this, is centuries ago, as we became a seafaring species, it became increasingly important that we figured out how to understand and predict the weather. That's crucial. You're going to navigate the globe, and you can see, as a species, as we're going to move out into our own solar system, the idea that we need to understand what drives all of that weather is equally important.
Okay, what we're going to do here, we're going to go ahead and close out. And before I do any final comments here, I want to turn it over to Jeff Newmark for some final comments.
Thanks, Wayne. Well, I hope we gave you a little bit of a taste of how exciting MMS is going to be. The complexity of developing this mission is just really unprecedented. 4 spacecraft, 100 instruments, each one 100 times better than we've done before, really enabling us to revolutionize our understanding, looking at this area that Jim showed you of magnetic reconnection that we've never been able to sample before. using our magnetosphere as a natural laboratory to study this. We're just very excited, and I hope you continue watching us on this journey.
And I want to thank our panelists. I want to thank the folks joining us on the phones here, and particularly on social media. Join the conversation on Twitter, Facebook, and go to the website. You'll be seeing a lot of updates and a lot of additional information as we get closer to launch down in Florida at www.nasa.gov/MMS. Magnetic Reconnection. I like to call this Class 101. The advanced classes will be down in Florida. It's phenomenal science with a phenomenal team. We will see you down in Florida. Thanks to the contractor team and the launch team. We're ready. We'll see you in Florida March 12th. Thanks for joining us from NASA headquarters. Goodbye.